Good morning, everyone. Okay, we'll start in a minute or so. If you have any questions, let me know. Any questions from anyone? Anyone with any questions? Okay, all right, let's start then. Just give me a second. Okay, I'll switch on my second device, put the chat window up. Am I audible to everyone? Yes, people. Can you all hear me?
Yes, I mean, we can hear you.
Thank you. Okay. All right, I'll change my name. So if you want to write, I mean, if you prefer writing, so you can write to this account called as Mentor. I'll just rename it. Okay, now you can write to Mentor if you wish. Okay, let's carry. Okay, so in the last session, we were discussing k-nearest neighbors and how to optimize it to the fullest. So we will see that today. Let's import the basic libraries. Okay, let me import matplotlib as well in case I need plotting of some kind. And let me import warnings. So I don't like looking at warnings. So let's just filter all the warnings that we get. So you will not see those pink messages. So if you run some functions, let's say if the function is getting deprecated. Okay. So in that case, put warnings dot, sorry. All right. So let's take a small data set for regression and let's tune it to the fullest. Okay. Okay. Last time, which data set we took? There is this diabetes data set and there is this exercise data set. Okay, let's continue for this diabetes data set then. Okay, so I'll just import it quickly. I hope you remember the syntax. So go to sklearn datasets, import the dataset, create an object of it, and then you can use this object to look at different properties. So these are the properties that we require. Okay. Now we'll be using only a few of these properties. So the features are in this data, and the output is in this target. Okay. And if you want to know the feature names, these are your feature names. So using these 10 features, we have to determine the impact of diabetes on the health of an individual. If the output is more for an individual in comparison to some other, we will say that that person has been affected more. Okay. So let's put it into a nice data frame. And the column names will be these column names, the list of feature names. Okay, so I'll just put it into this nice data frame. And now I hope you remember that the feature scales were very different. So if you describe this data frame, you see that, okay, let me take the transpose and okay, look at this. So if you look at the features on the row side and the descriptive statistics on the column side, look at the minimum and the maximum. I'll just print the minimum and the maximum. So you can see that the feature scales are very different. So we should either normalize or standardize. Better to do normalization. Okay. Okay, better to do normalization in the context of k nearest neighbors. Okay. So the method of feature scaling would be normalization. All right. So we will do this like when we figure out like the best combination of k nearest neighbors. So I hope everyone remembers what are the parameters that we need to fine tune. What are the parameters that we need to fine tune? Anybody who remembers? So I want to make the best k nearest neighbors model. So what are the things that I should check for?
Number of neighbors.
Number of neighbors. Okay. So let's say I'm checking in the range of say 1 to 15. Okay. What else comes to mind?
Distance metrics.
Distance metrics. So I'm going to check for some of the distance metrics like Euclidean, Manhattan. Okay. Say cosine. Okay. There are many different ways of using these similarity metrics. Anything else?
Weighted or
simple averaging. So uniform is for simple averaging, taking the mean, and distance is for weighted averaging. Okay, so these are the things basically I have to tune. I have put everything in a dictionary, as you can see. So this dictionary of parameters I'm going to pass to my k nearest neighbors model, and you will see a function which can you can say tune it to the fullest. Okay, and which is that method? We discussed it yesterday. Which method should we use to test the performance, like to compare, let's say, two k nearest neighbor models in an unbiased way?
R2 square and
no, R2 square is the you can say it's the evaluation metric. I'm asking which method is used to compare two machine learning models in an unbiased way. When I say unbiased, I'm talking about the way you evaluate the models. K-fold cross-validation.
Yeah.
K-fold cross-validation. Okay, so we are going to use this K-fold cross-validation. What that essentially means is we are going to break your data into some number of partitions. Every time one partition will serve in the test and all others will serve in the training. Okay, so if you want to use that, go to model selection. Okay, you require two methods. One is called as K-fold. This is the method which will break the data into multiple partitions. Okay, so K-fold is the method which will only break the data into multiple partitions. Okay, and there is this one more method which is called as grid search CV. What this method does, this uses the partitions one by one and trains models on these parameters. So K-fold is the method which will just make the partitions. Grid search CV is the method. You can say that we are searching in a grid of parameters. Okay, grid is nothing but a n-dimensional array. So we have a 3-dimensional array, and every dimension takes some values. So this is say 1 to 15. Okay, this is 3 and this is 2. So the first dimension has 15 things to look at, the next dimension has 3, the next dimension has 2. So how many total number of combinations am I checking? Think about it. How many total combinations would this grid set CV check?
90.
90. Absolutely right. Okay. And each of the 90 combinations will be checked how many times? K times of K fold. Whatever number that you will specify, how many times you want to do it. So if you want to do it, say 10 times, 10 folds. Okay. So you will specify this K fold with the corresponding number of splits, the number of partitions. I'm specifying it as 10. So it will break your data into 10 parts. Is that part clear? So every combination will be checked 10 times. Okay, and you will see the average of it. Okay, I'll show you just one function. Okay, I'll show you one function which will give you an insight about what this K-fold does. Okay. All right. So see, we don't need to do this, but I am going to show you what K-fold actually does internally. Okay. So let me show you the documentation of K-fold. Okay, I just need one specific. Okay, 1 second. Sorry. I need one specific property of it, which is, I believe, called as split. Yeah, this is the property that I need. Okay, just give me a second. Okay, let me show you what it does. So this is just to show you what K-fold does internally. So please listen to this very carefully. So if I create 10 partitions, okay, so I'm going to take say 100 samples in my data. If you look at this X is my data, right? I'm going to take 100 samples. So I'm taking these 100 samples. Okay, you can see I've taken 100 samples. Okay, so the first partition will have what as the train index? Okay, what will be the test index if you have 100 samples? What will be the test index?
9.
0.
0 to 9.
Yeah.
0 to 9, and 10 onwards, 10 to 99 will be train index. Okay, so that will be for fold. You can call it fold 0. Okay, because in Python indexing starts from 0. Okay, so what will be the indexes for fold 1? What will be the test index?
From 10 to
10 to
19.
19.
9 to 19, right? So you will see those things. Okay, let's see this. Okay, look at the first one, test index. This is partition 1, 0 to 9. Do you see that? And the test index is from 10 to 99. This is what you all said. Okay. Similarly, if you look at fold 1, this is the test index from 10 to 19, and everything else is in train. So do you realize what this K-fold is doing? It is dividing your data into 10 parts and taking the first part in the first fold as the test set and everything else in the train. In the second time, in the second fold, it takes the second part in your test set and everything else goes to train. So is this clear?
Yes.
Okay. So this is what it does internally. It generates the train and the test indexes. Okay. So if I have the train and the test indexes, don't you think I can get the data for every fold? All I have to do is this, right? So I just have to say X of my say train index. Okay. Using all the features. So this will become my X train for that fold. Yes or no? Does that make sense? These are the training indexes, right? For that fold. And what will be X test? X test will be nothing but X of this test index. Okay. And all the columns, because I want all the features. Okay. Same thing you can do for Y train also, because you want the outputs also, right? The outputs will be at the same index. Does this make sense? Yes, people. Since there is one output, you don't need to specify column there. And Y test is this Y of this test index. Okay. So I'll just comment this part out. I mean, if you want to use this syntax can be used. Okay. And you can train your model in every fold. if you want to use this. This is very clumsy in my opinion, so I don't use it. Okay, but you can use this as well. Okay, I would recommend you use this syntax. Okay, this is super easy to use. So look at this. Okay, let me show you for one parameter combination. So let's say my model is this. Let me import this k nearest neighbors. So I guess sklearn.neighbors. Import this k neighbors regressor. Okay, I'm going to show you with one parameter combination how do you train it. All right, so let's take the number of neighbors to be maybe say 3. Okay, I'm just using this combination right now. So this is my training data. This is my test data, y-train and y-test. Okay, we have to normalize our data, right? So let's import min-max scaler also, which is there in pre-processing. Okay, so let's import this min-max scaler. Any specific range that you want me to scale in? Or can I do it in any range? Any range is fine. Let's say -2 to 2. Okay. So apply this min-max scaler, first fit it to the training set, and then you can transform the training set and save it into say transformed X-train. So see, please note that this is happening in every loop. Okay, and similarly, you transform the test set as well. And now you can train this model inside this loop. So model.fit, which is your k nearest neighbor model. So this model is now fit, okay, on this transformed data that you get and the corresponding outputs. Okay. So once the model is fit, I may want to compute some, you can say some measure out of it. Which measure do you want me to compute? What measure do you want me to compute? Yes, people.
Sum of absolute error.
Sum of absolute errors. Okay. If you want to compute sum of absolute errors, what you need to do is you have to import mean absolute error and multiply by the number of samples, because sum of absolute errors does not exist as a explicit metric. Okay. So let's say I'm going to store my mean absolute error, okay, in a list. Okay. Sorry, sum of absolute error you said, right? Okay. All right. So this model will evaluate first, and then I'll get the predictions from the predict method. So I can pass the test set and it will give me my predictions. Okay. It will give me my predictions. Let's save it as spreads. And now I can evaluate this mean absolute error. Okay, and pass the actual values, and the predicted values are in spreads. And since you want sum of absolute errors, I should multiply this with the number of samples in the test set, okay, on which the mean absolute error is computed. And I will append this to the sum of absolute errors list that I created. Okay, so how many values will this sum of absolute errors have? How many values will this sum of absolute error have? Any guesses? How many times will this process run? Think about it.
It will be a list where each list will have.
No, it will be just a list of single values, not a list of lists. It will be a single list. I am using only one combination. Please look at this carefully. I am trying to evaluate this on the 10 folds. So how many sum of absolute errors will I have? One model, I am doing it for 10 folds. So how many values will I have?
10.
10 values. Okay, so you'll see 10 values in sum of absolute errors. Okay, so this is done. So these are your sum of absolute errors. Okay, the 10 values that you see. Okay, I mean, if you want to see how many values are there, just type len of it. Okay, so these are your sum of absolute errors for the 10 folds. Do you see that sum of absolute errors is different for different folds? Yes or no?
Yes.
So the argument, if you remember, I made this argument initially that if I take a different train test split, the results can change. And you can see the results change drastically, right? In some of the cases, the results are very, very different, even for the same model. Okay. So it is not wise to say, if we do a single train test split, we cannot compare two machine learning models. That's why we are doing it, say, 10 times here. So I want to use the mean. So this will be the performance. Sorry, this is a list, right? To compute the mean of a list, I can actually sum it up. So I can do the sum of it, and then I can divide by the number of elements in this list, which is len of SAE. Okay, so this is your mean sum of absolute errors. Okay, you can call it mean of sum of absolute errors for the 10 folds. So this is the actual performance of your model evaluated over the 10 folds that you did. Is this clear? Yes, people, is this clear?
Sandon, I have a doubt that where we were using the min-max scalar to normalize the data, and then we were transforming it, right? So what this transforming, can you please?
Sure. See, when you fit the model, okay, what is meant by normalization? What is the formula? If you remember, how do we normalize? If you remember, can you tell me what is the process of normalization?
Normalizing the data, it could not have a much difference, much distance between the numbers. So it has to be normalized with the same distance so that our data will create a good, a bell-shaped curve.
No, that is standardization. Normalization is constraining the data in a given range.
Yeah.
So currently we are constraining the data in this range of -2 to 2. Okay. So how do we normalize? We actually subtract the minimum value and divide by maximum minus minimum. For every value that I want to normalize, I will subtract the minimum of that feature, divide by maximum minus minimum of that feature.
Okay.
Do you remember this? So if you don't remember this, then you'll not get this. Okay.
Okay.
All right. Again, I cannot repeat the whole concept. I request you to please revise that. But I'll tell you this. Okay. The steps in normalization is, first you find out the minimum and maximum for every feature. And that is what you are doing when you are applying the fit function. So this fit function computes the minimum and maximum for every feature. Okay. If you want to see where the minimum and maximum is stored, you can actually print that. Okay. If you want. So there is this property called as mm.min, and you can print the minimum and maximum also. If you want to see, okay, what this function is doing.
Okay.
So it computes the minimum and maximum, and first, then you apply transform. What transform does is, it uses the minimum and maximum that you computed from every feature and applies it on all the values and generates the transform data. So this transform data, for every feature, you will see the range of -2 to 2. All the values will be squished between -2 to 2.
Okay.
In the training set, previously the values are different, right? You can see.
Yeah.
Okay. The minimum and maximum ranges for age is around -0.107, and this is 0.11. I am putting it to -2 to 2. Okay. I am putting it to -2 to 2.
Okay. So you are transforming it in between -2 to 2. Okay.
Correct. That is what we are doing. Okay. Using the same values of the minimum and maximum values of the features in the training set, we are transforming the test set as well. Okay. You have to put it, ensure it in the, we have to ensure that they are also in the same range, right? When we apply our check, like when we predict on the model, because model has been trained on a feature set with -2 to 2. So test set should also be within the same range, right? Yes or no?
Yeah.
So that we do it for the test as well. And then we are evaluating the model, okay, using this predict function with the help of some of this mean absolute error. Since I think one of them one of the participants asked me to evaluate it on sum of absolute errors. I'm multiplying this number by the number of samples. So the number of samples into mean absolute error will give you sum of absolute errors. Okay, so we are storing all these absolute errors in this list called as SAE. Since we are doing this 10 times, this SAE contains 10 folds. I mean, the sum of absolute errors for these 10 folds. Okay, and since there are 10 values, I have to choose a representative of these 10 values, right? So I choose the mean. So this is like the performance for 3 neighbors. Okay, when the number of neighbors is 3 on 10 folds. Okay, you will say 549.06 is the sum of is the average value of the sum of absolute errors for 10 folds. Okay, can you compute the same for say 4 as well? You can do that, right? Let's say I do it for 4. Just see the values. Okay, I want you focus on this value. Okay, what this value changes to. So it changes to 546.1. So did it improve or did it worsen?
Improved.
It improved, right? Lesser the better. Okay, so which is better now, 3 or 4? 4, right?
4.
Okay, and so you don't have to do this using a for loop. Okay, see, I can run a for loop like this, right? I can put all of it. Okay, I can put all of it. Let me do it like this. Okay, so I can run a for loop on say the number of neighbors. Let's call it as k. So for k in number, let's say a range of 1 to say 16. So I'm checking for 1 to 15. Okay, for say type of metric that I use, let me call it MET. For MET in Euclidean cosine and this. Okay. Okay, for Euclidean cosine and this, let's again. Okay, and let's say for averaging type in this particular metric, uniform and distance. Okay, I'll compute everything inside this. Okay, I'll compute everything inside this. All right. Now, how many values? So currently we are storing these 10 SAE values, right, for one combination. So let me store the average results. Okay, let me call it sum of absolute errors per combination. Okay, so per combination, I'm going to create a separate list. Okay, so in the per combination, I'm going to store the average. Okay, in the per combination, I'm going to store the average. So this would be, I'm going to append these averages which I computed. Okay, these averages which I computed. Okay, and I'll print it as well so that you can see. Okay, I'll print this as well. Okay, let me just print this as well. So I'm going to print the combination. Okay, 1 second. Let's put everything inside. So this is the model that you have. So number of neighbors is this k. Okay, and your weight, sorry, metric is this is MET. Okay. I called it as MET, right? Okay, and the weights is this KVG type. Okay, so I'm going to use this model to evaluate the results for 10 folds. SAE contains those 10-fold values. I'm saving the average of those 10-fold values in this SAE per combination. So per combination, I'm storing the average of the 10 folds. Okay, let me print it as well. So the combination is, okay, look at this. So the combination is this. So let me start the combination. Okay. So combination is, the first thing that I want is this k, the number of neighbors. Okay, then I have MET. Okay, and then I have what is the name of it? AVG type, right? AVG type, and I print the mean, the sum of absolute errors per combination for it. Okay, do you want me to print the SAE also? Do you want me to print the 10-fold results, or do you just want me to print the mean? What do you recommend?
Just the mean.
Just the mean. Okay, let's print this SAE per combination. Okay, just the mean of it. Okay, so this is your combination. Okay, 1 second. So I'll just close it. This is the performance. So let's say this is your sum of absolute errors, the average sum of absolute errors. Okay, and this is it. And let me put just a backslash n. here in the new line, and the separator I want to be in basically nothing, because I want it to be like close by. Okay, 1 second. All right, I think it looks nice. Okay, so this is the combination and the results. Okay, so how many results will I get now? How many results will I get now? I need to initialize a count as well. Okay, just a second. So this counter will store how many combinations I'm running. Okay, this counter will store how many combinations I'm running. So can you tell me how many combinations will I be running? Yes, people, how many combinations will I be running? Think about the number of combinations. 90. So this code is going to run 90 times, essentially. For each of the 90 times, it is going to print these combinations. I mean, the sum of absolute error for each combination. Let's see this. Okay. I should have put a comma. I forgot to put a comma here. And let me print the count also so that you can see which combination it is. Okay. So let's say this is the combination number. Let me print. Okay. Combination number is let's say the number combination number. The first combination number, let me print. This is your C. Okay, this is your C here. I called it count, sorry. Okay. The first combination count, and this is this quote. Yeah, this is okay. Okay, let's once again, there is this comma is missing here. Okay. And maybe put a space here. Okay. Are you able to see what's the combination number 0 and all? Yes, people. Are you able to see this? So the combination, I am printing the combination numbers. Okay. And I am printing the corresponding sum of absolute errors for it. Okay. Now, if I ask you which combination is doing the best, so I can actually do this. I can go to my sum of absolute errors per combination. Okay, these are for of the 90 combinations. If I ask you which is the best combination, should I pick the minimum value or the maximum value?
Minimum.
Minimum.
Value. So let me get the minimum value from this. So this is the minimum value, and I want to get the index of the minimum value. Okay, so I can use this SAE per combination. So if I want to get the minimum value from a list, okay, there is this property called as index. But this property will pick the very first index of the, so if there are two values which are the same and they are minimum, it will take the very first index. Okay. So this is at index 50. Let's look at the index number 50. What is the index number 50? Do you see? This is the one.
494.
494.499. So 9 Manhattan and uniform is the best. Okay. I'm going to show you. You don't have to do all this stuff which I wrote here. Okay. You don't have to do all this stuff which I wrote here. Okay. There is this method called as grid search CV which can do it for you. Okay. Shall we do this now? This is the equivalent of what I just did. I ran it for every possible combination. Okay. Used k-fold to get 10-fold results, took the average and stored it. And now I'm returning the best combination index. Okay. It will, so if you put all the combinations in a list and maybe say a list of tuples and get the 50th tuple, you will see this tuple, which is, what was the name? 50th tuple is 9 Manhattan and uniform. You will see these results, by the way. Shall we apply it and see, okay, this is what we get? Yes, people. Shall we apply it and see, this is what we'll get?
Yeah.
Yes.
Okay, let's see. You'll get the same thing. You'll get this.
Okay, so this grid search CV will do all this 10 line of coding in a single
Correct.
word.
Not in a single word, but yes.
Okay.
Okay. Not in, it'll just need 2-3 lines.
Yeah, I get it.
2-3 more lines. Okay, just 2-3 more lines. Let's look at this. Okay. So make your model. Your model is this k neighbors regressive. Okay. All right. So how do you use, let's see how to use this grid search CV. So pass the model to it, because the model will be evaluating the results on every fold. The name of the parameters, the list of your parameters is to be passed to this argument called as parameters grid, okay, which is this params. It has to be passed as a dictionary. Okay. The type of cross validation technique is k-fold. So this is kf. And let me ask you this. If sum of absolute errors, okay, is the minimum at index 50, do you think mean absolute error will also be minimum at index 50?
Yes.
It will be, right, because it is nothing but the multiplication of the number of samples, right? Okay. So the reason I'm saying this is because the scoring metric here, which evaluates the model performance, you don't have sum of absolute errors. You can only use mean absolute error here. But please note this. Okay, there is this one catch. Do you remember I talked about negative and positive metrics? So mean absolute error is a negative metric or a positive metric?
Negative.
Negative metric, lower the better. This method, grid search CV, it does not accept positive metrics. So how do I convert this mean absolute error to a positive metric?
Negative sign.
Negative sign. So this is the name of the method that you will use, negative mean absolute error. It's computing the same thing, but with a negative sign. So in your results, you will see the value as negative. Okay, in your results, you will see this value coming out to be, 494 into 499 multiplied by 10. Okay, you will see 4944.9999. Why am I saying this will be 494 into 9999? Any guesses? Why am I saying this would be the number 4944.9? Because you'll be multiplying it with the number of samples, and the number of samples are how much?
100.
No. In this, no. It's not 100. Is it 100 right now? Yeah, it is 100 right now. So every test set will have 10 samples, right? Yes or no?
Yeah.
So you'll be multiplying this number with 10 to get the. You'll be not multiplying, dividing it. Sorry, it will be 49.49. My bad. See, we are getting the negative mean absolute error, right? It will be dividing it by 10. My bad. So you'll see 49.4499, hopefully, with a negative sign in front. Okay, let's see this. Okay, so this is the grid search instantiation. And what you have to do is just fit this grid search onto the first 100 samples that I took. Okay, and the output will be for those first 100 samples. Okay, output will be the first 100 samples. Is this part clear? Yes or no? Any questions up to this point? Is this clear? Yes or no?
Yes, sir.
Okay, now there is one catch. Okay, and there is something which I'm not doing here. What is it that I'm not doing in this code? But I did it here in this code. Okay, let me give you the hint. This. What is this? What is this piece of code doing?
It was transforming the data into a
Normalization, right? So am I doing normalization in this code anywhere?
No.
No, right? So that is the catch here. So if you want to do normalization, okay, you need to use a specific syntax, okay, which is called as, you need to use basically first we want to normalize our data for every fold, and then we want to apply the model. So this is like a sequence of steps, and a sequence of steps in machine learning or in data science is called as a pipeline. Okay, so we'll be using a pipeline to normalize your data and then apply the model. So you can use this pipeline for many different things. So for example, if there was a data set which had null values in it, and you want to impute the null values with the mean. So first you take an imputer which will impute the null values with the mean, then you will transform the data, and then you will apply the model. So whatever steps that you want to do, you can define it with the help of this pipeline. So I am only interested in first doing the normalization, and then I'm interested in doing the application of the model on my, you can say, every fold. And that is what I'll do. So look at this. And the name of the function is pipeline also. It's there in the pipeline class, and the name of the function is pipeline. And the pipeline takes these steps that you will define. Okay, so I'm going to define my steps. So let's say my steps are, every step has to be defined like a tuple. Okay, every step has to be defined like a tuple. So the first step is doing normalization. So give the first step a name. I'm calling it as mm. Okay, I'm calling it as mm. All right. So this is the min-max scalar. In what range do we want? 2, 2, right? We want to compare the same results. So my range is this -2, 2. Okay. So that's the first step. My next step is application of the model. Let's call our model as k nearest neighbors, or KNN for short. And this is the model that I want to apply. Okay. This is the model that I want to apply. Okay. Is this clear? Yes or no? Is this clear?
Those MM and KNN are just the short forms that you're using?
No. You give it any name. It's just the name of the model. You can call it model also if you want.
Okay.
Okay. You can call it anything. You can call it ABC, whatever name that you get. Okay. These are not the short forms. These are names that I defined. Okay.
Okay. Yeah.
All right. So pass these steps that you created, the my steps, to these steps. And you can call this pipeline to be, say, your sequence of steps, your pipeline. And instead of the model, you pass the pipeline to it. Okay. Is this part clear? Yes, people. Up to this point, is this clear? Any questions here?
So that M pipeline stuff, can you please repeat it
Yeah.
again?
See, the pipeline will be the sequence of steps that I perform on every fold. So grid search is going to do the process that you define, right? That you are defining as your sequence of steps. So instead of your model now, you have to pass the pipeline. I'm calling this pipeline with the steps that you created as m_pipe. See, if this is not clear, you use this and pass it here. Is this clear? I mean, I just created a name for it. Okay. Is this clear?
Yes, sir.
Okay. Do you prefer this syntax or the previous one?
The previous one also was good.
Fine. Okay. All right. All right. Okay. Now, okay. Please note this. See, grid search CV is now going to handle this pipeline with the list of these parameters. How will grid search CV know the parameters that you have specified are for which of the sequences? I mean, for which step? See, can you tell me these parameters are for which step? The first step, which is min-max scalar, or the k nearest neighbors? Can you tell me these parameters that I defined are for which step? The first one or the second one?
K and
Second
1.
The k nearest neighbors one, right?
Yeah.
These parameters have to, but grid search doesn't know this, right? Am I passing any of that information to it? No, right? It is not that intelligent. It will figure out, okay, see, because I can pass these, okay, look at this. Don't you think I can pass feature range as a parameter also? Yes or no? I can pass this feature range as a parameter. The first range is -2 to 2. Maybe say the next range is -5 to 5. Yes or no? I can pass this also, right? How will the pipeline know? How will this grid search CV know that feature range is for what? Because I know feature range is for min-max scalar. Does this make sense? So how do we do that? So the only thing that you have to do is this. Okay, please keep this in mind. Whichever parameter are there for, like, so if this parameter is for this k nearest neighbor, use the name that you gave. You gave the name as KNN, right? Use the name as KNN and give 2 underscores. Okay. So this is also k nearest neighbor parameter, give 2 underscores. KNN parameter, give 2 underscores. But this is min-max scalar parameter, give 2 underscores. So how many combinations will be tested now in total? I just added one more parameter combination, feature range, 180. So out of those 180 combinations, whichever is giving you the highest value of negative mean absolute error, that will be chosen. See, previously we were choosing the minimum value, right? But this is a positive metric, higher the better. Okay.
But will
Yes.
my feature range have any impact on the
No,
model?
no, it will not. But I just kept it so that you can see what is happening.
Okay.
I just kept it so that you can see, you can realize, okay, this parameter is for feature range. Okay. All right. Let's see what it returns. Hopefully, what it will return is this combination, the one that we got, which is 9 Manhattan and uniform, and the output for that will be 49.44. Shall we see that? Okay, let's see this. Okay, this is doing its job. Okay, let's wait for some time. Okay, it is done. Okay, now if you want to see what is the best parameter combination, you have to type gcv.bestparams. This is the best parameter combinations amongst all. Okay, do you see what we got is the same thing? Manhattan, 9 and uniform. Yes or no? Do you realize this? The best thing that we got is the same thing as this, right? The feature range is -2, 2. Is this clear?
Yeah, the same.
Okay, the same. Let's see if we get the same score as I told you. It will be 49 point whatever this number is, 49.49 something. Okay, let's see this. So GCV dot best score. Do you see that? See, whatever I have taught you, right? See, these are the things that are implemented by these functions to the core. Okay, but the way they are doing it, they are trying to minimize the lines of code for you. See, I wrote so much code here, right? Yes or no? Okay, in comparison to this, I just wrote maybe 6 or 7 lines. The most of the time it went in defining these parameters. And so on the above case, yes. Yes.
Like there we see is like the decimal is after 3 digits, 494.999 something. Here we are getting the decimal after 2 digits.
You actually missed me in between. Okay, what is this? What is SAE?
Oh, okay, I get you.
So this is sum of absolute errors. Okay, and what am I doing right now? Mean absolute error. So this should be multiplied, divided by 10, right? If you want to, I mean, this value, if you want to get the mean absolute error from it. Okay, all right. See, I can compute the mean absolute error also if you want. I'll just need to change this a little bit of code. Okay, 1 second. Let me call it say MAE per combination. Okay, I just need to change one thing and you will see the same results. I'll just remove this part. So this is now storing the mean absolute errors. Okay. So somebody asked me to compute sum of absolute errors. That's why I did that. Okay.
So just to check my understanding.
No, yeah, that's fine. That's fine. Okay. See, I don't mind that. I don't mind that. Yeah, I don't mind that. Okay. I want to show that. Okay, you'll get the same thing. Yeah. All right. Looks all right. Okay, let's see. Okay, these are all the combination values. This is the best MAE per combination. Any mistake that I did?
In the above code, can you just scroll up?
Yeah.
This is MAE append in the append line, sum of MAE.
So which line? This one?
Next to this.
This line? Yeah, this is oh yeah, I shouldn't use SAE then. Thank you. Yeah, I missed this part. Okay, all right. Thank you. Okay. All right, this is your MAE per combination. Okay, let's look at, so the 50th combination would be the same, but the value would now be, look at the 50th combination. Do you see that now? It is 49.44.
Yes.
Okay, so we are doing essentially the same thing. That's what this function is doing. Okay, both the functions are essentially doing the same thing. Now, if you prefer this, like writing from scratch, use this. If you want to do it from inbuilt functions, use this. Okay, is this clear?
So in a real-time scenario, mostly we'll be using
the latter one. Yeah, this one. Okay, this is much more convenient, right? Okay, and you can add a lot of other things in between. I mean, if you want to define more steps, put more steps here before this. Okay, there are so many ways, in which you can make your life convenient. Okay, is this clear? By the way, you don't even have to do this. Okay, let me show you. See, I am running this method 10 times, right? Yes or no? This part, I'm running this method 10 times. Even there is a function for this as well. So let's say I give you a model, okay, and you want to get the performance for that particular model just 10 times. Okay, so let me show you this. Okay, so this is the best parameter combination that I have, right? Okay, and this is my best model. This is also called as best estimator. This is also called as best estimator. Now, which out of the pipeline, what is the best estimator? I mean, the model number is what? So which step should I consider in this best estimator? It's a pipeline, right? Do you see that? What should I do? Tell me. Yes, people. See, let's say if I want to print the first, like the first step, the min-max scalar, you can simply print this. If you want to print the model, you can simply print this, the name that you gave. Okay, you can actually print it via indexes also. Okay, you can print it via indexes also. Look at this. You can, if you print 0, it will print the very first step, which is the feature range. Okay, and if you print 1, okay, it will print the next one, which is your k nearest neighbor model. Okay, you can print it using the name that you got and the steps that you got. Okay. Now, my question is this, look at this carefully. This is the best estimator that I have. Okay. All right. Assume that now I want to apply it onto a different data set. Okay. So what should I do? I want to apply it on a different data set. What should I do? Let's say I want to test it on a different data set. If I have another test set, how do I use this? Okay, which method do we use to make predictions on a test set? Tell me, which method do we use to make predictions on a test set? Predict, right? So if I want to use the best model that I get and I want to test it on a different test set, okay, so get the model that you have. Okay, this is the model, right? GCV.best estimator of 1. This is the model, and you can use this model to predict on any set that you have created. Okay, on any set that you have created. So let's say I want to test it, okay, on say, so I think I have transformed some of the data already, right? No, I haven't. Okay, so what I'll do is I already have my min-max scalar ready, right? Okay, so this is my min-max scalar. I can use it like this: GCV.best estimator of this 0, or you can call it MM also in this case if you want. Okay, and this is your k nearest neighbors. So I'm going to use this best estimator to transform some of the examples. So I'm going to transform some of the examples, and the examples that I'm going to use are say from 100 to 200. Okay, so I'm testing on 100 examples, the next 100 examples. Okay, so this will give me my, let's say, test set. Let's imagine this is your test set. Okay, and so I can pass this test set, which has been normalized in the range of 0 to 2, and this will now give me how many predictions?
100.
100. So you'll see you'll get 100 predictions. If you want to now evaluate, okay, let's say these predictions, how do you do that? Use the mean absolute error, any evaluation metric that you want. Let's say I want to use, okay, the mean absolute error to, so these are my predictions. These are my actual values. So actual values will be present in this y of 100, 200, because these are the next 100 samples, right? Okay, so these are the actual values. I want to compute, say, the mean absolute error for it. So this is how you can compute the mean absolute error. So this way you can utilize the best model that you get, okay, and predict it for any unknown data also. See, later on you'll be deploying it, right, somewhere. Once you find the best model, you'll be using it in the real world. Okay, so you'll have to use the predict function on the new samples, right? You'll have to use a transformer, the scalar, on the transform data. So that's how you do it. Okay, is this part clear? Any questions here? Ask. Okay, these things are very important. See, I don't want to rush. Please tell me if this is clear or not. I'll repeat it otherwise. Okay, if you can you tell me if this is clear to you, at least, like those of you to all those, if it's clear, can you say a yes? Yes, this is clear. At least one
So
or two.
please repeat it again.
Okay. See, I got the best model using this GCV, right? Grid search. Yes or no?
Yes,
I
sir.
found the best model. This was the best model that I got. And what is the best model? It is actually a pipeline. Okay. What is this pipeline? Pipeline contains two steps. First, it normalizes, and then it applies the model. Okay. So I want to test it on a new set. Okay. So I chose a data set on which I want to predict. This is the data set that I want to predict. This is the next 100 samples. Okay. This is the data set that I want to predict on. Okay.
So like initially we used the training set. Now we are implementing the same model for the test set.
We are using the best model that we have obtained. Okay. And we want to test it on some unknown data that was not even a part of our data set.
Okay.
Okay. See, when I called this grid search, on how many examples it was called? This will tell you. It was called on the first 100 examples of your data set. Okay. So did I look at 100 to 200? No, right?
No, 100.
Okay. So I'm just saying
200.
I use this 100 to 200 set. Okay. I kept it later on so that I can show you if you find the best model using a limited data set and then you use that best data set. Okay. The best model. Okay. Onto a new set. This is how you do it. So first you have to scale your data. See, this data is not scaled, right? X of 100 to 200. Is this data scaled, by the way, when I gave it to you like this? No, right?
No.
So first I'll be using the transformer, the scalar that we got. So the best scalar was what? In the range -2 to 2, right?
Yes.
So I use this scalar, use the transform function from the scalar, transform this data and ensured that it is now in the range of -2 to 2, depending on what the minimum maximum from the training set were. And now I'm using this k nearest neighbor model to predict it. Okay.
Okay.
If you had the actual values, because I do, if you had the actual values, you can compute mean absolute error from it or any other metric. Okay.
Okay.
See, ultimately, what is the point of getting the best model? You have to keep it somewhere. Let's say you'll be deploying it as a web application, right? Let's say you're running a website and you want to use a machine learning model to predict something. So you'll be deploying it on your website, right? Yes or no? You'll be using it as a part of your application. So how do you use the best performing model? What the data might be incoming in the raw shape. Okay, or let's say if you have structured it, then you'll have to first scale the data in which the model was trained. So first use the scalar on it and then apply the model. So this best model is now something that can be used, okay, on any data set. Okay. Is this part clear?
Yes, sir.
Okay. Anyone else to whom it is clear? See, please ask. Okay. These are so I can understand these are non-trivial things. So if you are still stuck, please ask. Okay. Is this good to go? Shall I move to the next topic?
Yeah.
Okay. Now let's try to understand. Okay, what will happen if this was a big data set? See, I'm just using 100 samples. Okay, right now, imagine in my data set, if I had 1,000,000 examples, what would you do? Is this viable to do it? Is this feasible to do it? You're checking 180 combinations. Let's say your data has 1,000,000 examples. Your X and Y, they are 1,000,000 examples. The number of samples in those are 1,000,000. Do you think it is viable to do it? Or is it feasible to do it in a matter of, say, 1 hour?
No.
Time consuming.
It will be very time consuming. You are going to check 180 combinations. Okay. Trust me, it will take you at least 8 hours to do it. 8 hours is just a small number that I'm saying right now. It might be even more depending on the number of features that you have. Okay. So, I mean, nobody wants to wait for 8 hours. So is there any alternative? What do you think? Is there any alternative? I mean, how can you reduce the time? Can you give me some suggestions? Instead of looking at all these 188 combinations, can we do something else to save some time?
Can we parallelly process?
That you can do, okay, that you can do, but that will only give you maybe say saving of 3 times maximum. It will, I mean, if earlier it took you 8 hours, then it will probably take you say 3.5 hours or 4 hours. Okay, I mean, you cannot get a speed up of 10 times or 20 times if that's what you're thinking. But I get the point. Okay, something else from like basic standpoint. Forget about parallelism. But yes, if you want to parallelize, there is this argument called as n jobs that you can use here. And you can set it to -1. This will utilize all the cores in your system. Okay, I don't recommend it because if I do that, my Zoom will stop. Okay, it is there in the model training as well. Okay, it is there in the model training as well. You can specify here as n jobs and you can set it to -1. Okay, you can specify here also. All right, but that takes the advantage of parallelism, but I cannot do it. My Zoom will stop and the call will probably get disconnected. So any other thing apart from parallelism that you can think of?
You can
Okay.
split the data into 2 or 3 cores.
But then, okay, let's say if it earlier it took you 8 hours, okay, and now it will probably take you 7 hours each. So if you do it in 3 splits, it will be 21 hours. You are actually taking more time, not less time. Okay, let me ask a simple question. Do you think I can compromise on the best results and still achieve a desirable result, which is very, very close? And I have, if I reduce the time significantly, but I get the best performance or very, very close to the best performance by doing that, do you think that is acceptable?
Yes.
Does that make sense? Okay. Let me tell you something. How many combinations are there right now?
In which example you're saying?
In this current example, how many combinations do I have?
180.
Okay. Let's say I take 10 combinations at random out of these 180 and only check for those 10 combinations. Okay. If I'm lucky, I will pick the best combination. If I'm unlucky, what can you say about those 10 combinations? Can I, let's say with some certainty, can I say that one of those 10 combinations is going to be very, very similar to the best performing results? The performance of one of those 10 combinations will be very, very close to the best performing results. Yes or no?
Might be yes.
No, isn't this with high, like, I mean, the high probability? Do you think that, let's say, the best result that I got, okay, look at the combination results that I have. Okay, let me show you the combination results that I have. These are the combination results, MAE per combination. Okay. Okay, how many results are here in this MAE per combination? 90, right?
Yes.
Okay, I'll show you the sorted version for it. Okay. Sorry, I should write it like this. I can say numpy.sorted and I can sort this. Just a second. Sorry, in numpy there is sort. I could have typed sorted in the list. Okay. All right. Look at the top 20 values. Aren't they close by? I was talking about 10. Okay. So out of the 90 combinations, let's say we pick 5. Look at these 5. Aren't they close by?
Yes, it is.
Okay. So if I'm lucky, at least I will pick 1 out of these 5, right? In the 5 that I pick.
Yeah.
Very high. Okay, let's say if I do 10. Don't you think if I pick 10 out of 90 combinations, I'm very highly likely to get one of these results which are very close by? How far are these results, by the way, if you see that? And aren't they a good estimate of my model performance? Yes or no? They are, right? Do you realize it? See, if I can give you, see, this is just an estimate of how good the model is doing. Do you really care about these numbers? Okay, let's say if I give you the second best combination. Okay, if I give you the second best combination, wouldn't you still be satisfied?
Yes.
Okay, I mean, because you have to get the results in a limited time. So there is this trade-off that you have. So there is this another method that you can use. What this method does, so the steps are almost the same. What this method does, instead of using all possible combinations, it uses a subset of your combinations, exactly 1/10 of it. Okay. And the name of this method is randomized search CV. Okay, so instead of looking at all the combinations, okay, it uses only a subset of the combinations and gets you the results. Okay, the only thing that you have to change is a few things. Change the name of the method. Let's call it randomized search CV. The syntax is almost similar. Okay, the one change that is there is this: parameters grid is called as parameters distributions. Okay, rest everything else stays the same. Okay, I'm just giving it a different name. Let's call it RCV. Okay, let's call this as RCV.fit. If you are lucky, you will see the same combination, which was 9 uniform and distance. This was the best combination, right? 9 uniform and Manhattan. By default, the default value is uniform. That's why it's not printing it. Okay, that's why it is not printing it. The default value is uniform. That's why it is not printing it. Okay. So let's see. If we are lucky, it will pick that combination and will show us the results. Okay, just a second. What does it say? I made a mistake somewhere. Randomized. Oh, sorry. Randomized search CV. Here it is, correct. Okay, this is done. Can you see the speed up? See, previously it took around maybe a minute or so, right? If you remember correctly. Okay, let me show you. Shall I run this again just to show you how quickly, how much time it took? See, it's taking some time, right? Yes or no? And that ran like, so it took around maybe say 20 seconds. This one took probably around maybe a second. Okay, how fast it is. So it runs only on a few combinations. Okay, and let's see what is the best combination that this gives me. So this gives you the best combination as this. See, it gives me the same combination, but the feature range is -5 to 5. Don't you think we are lucky now? Yes or no?
Yes.
It's the same combination that we get, right? So we were lucky and we saved a lot of time. Okay. So, and if you look at the results, this will be the same results that you had earlier. Okay. 49.45, whatever that number was. Okay. Is this clear? So this is how you can work with randomized search CV. It saves a lot of time. If you're lucky, it gets the same combination. See, if you run it again, you might end up in a different best combination. Okay, I've just run it one more time. Let's see what is the best combination. You're lucky this time also it chose that combination. Let's see one more time. Okay, can you see that now it has changed?
Yeah, to the team.
Okay, and let's see what is the best score. See, very, very close. So it may be the third best or the fourth best combination that you have. Okay. I mean,
So
if you
can
see,
we
yes.
fix this, like what combine every time I get this, like we do random state.
Mhm.
This also can be fixed.
Yeah, this you can fix this randomized search CV. I mean, if you want to get the same combination, put a random state here. Okay. So if you want to replicate the results later on, you can put a random state here. Is this clear?
Okay. Yes.
Okay. I mean, this time you'll always get the same results. I don't recommend it, see, because if it takes so less time, you can run it twice or thrice, right? And then you will be convinced what is my best combination. Okay. Does it make sense? So you can still see I ran it for another combination. This time it is 15 distance in Manhattan. It is 50.212. Fair, still very close to 49.49. Okay. So that is the idea behind randomized search CV. Okay. If you're lucky, the same combination will be picked. If you're unlucky, then I mean, your results would still be very, very close by. Okay. Any
Like,
questions?
how could I
Yeah.
train my model? Like,
How do I?
got, 2 times I got distant neighbors as 9, which is a good model. Then I get 15 sometimes. I get 10 sometimes. How should I train my model to predict the values in future?
So whatever combination that you get finally, use that.
But every time I'm getting different combinations.
No, ultimately you will see the best score, right? Whichever. So let's say you run it 3-4 times. Okay. And out of those 3-4 times, you will see the best score also, right?
Okay.
Remember the combination and the one that has the least best score. In this case, the highest best score, because there is a negative sign in front. Okay, so pick that. Okay. Now, see, so this is a valid question that you asked, like not from the explicit standpoint, but I'll ask you this. Is it guaranteed that, let's say, if I go with this combination, which is distance 15 and Manhattan, and if you remember the best combination, that was uniform 9 and Manhattan, right? Do you remember that? Okay. So let's say if I pick this over the other one, is it guaranteed that that will perform better than this on an unknown set?
No.
No, right? So that's why I'm saying you can pick any of these.
Okay.
All right. So does it make more sense now to pick like any of the top 5 or any of the top 10? That's why randomized search CV is so useful.
Okay.
Because it is not guaranteed, right? On a new set, which would be better. Okay.
Even if I do it through grid search, I'm not guaranteed that that particular combination, which is best for my training data set, will actually be best for my testing one. Or my
You see here the data set that you have is split into train and test for every fold, right?
yes.
Okay. The model that you're finally getting, basically the set of parameters that you're finally getting, they are the best on those 10 test sets on an average.
Correct.
Does that make sense?
Yes.
However, on an unknown set on which you finally deploy the model, see,
Yes.
your model will be predicting on new examples, right? Beyond the data set that you collected.
Yes.
So on those, can I always claim that the best model that I get will always perform the best on new data which will come in? I cannot, right?
No.
The only thing that I can do is I can choose the best that I on the data that I have.
Best
But-
possible I can have. I cannot have the best thing.
Right. So that is not guaranteed to be the best on unknown, right? But so it's like saying that I have say 10 different athletes, okay, who are going to participate in a race, and let's say I know Usain Bolt is the best sprinter of the world. Do you think Usain Bolt will sprint like the best across like all the entire world in unknown conditions?
No.
May not, right? May not. But the only thing that you can do is you can rely on Usain Bolt.
Yeah.
Okay, so that is what we are doing here. But if you choose maybe say other sprinters like from Jamaica, which are still very, very close by, or maybe say Tyson Gay, who is the best sprinter from US, or maybe say if you know about sprinting a little, you can tell me some of the names. And
I don't know. I don't have it.
okay. So the idea is like we can go with any of the top 5 and it will still be good enough. Okay. All right. So these were some of the things that I said. The one thing that I can recommend you is go with less number of neighbors. Go with not with too less number of neighbors and not with too high number of neighbors. Okay. It has to be somewhere in the middle. So if you are confused between what model to pick, the number of neighbors that I suggest should be somewhere in the middle. Okay, not too high, not too low. Okay, and this is one concept that we'll talk about in detail. Okay.
So
yes.
in here, like we have used 3 nearest neighbors so far, right? So like in a like when it comes to an organization, or else if I'm training any module, so that time, like what is the minimum and maximum range of neighbors that I can have, or you suggest?
Okay, a good question. See, because the number of neighbors, if you think about it, maximum it can go to the number of examples in the training set, right? And that is a big number.
True.
So I would say you don't really have to go far. Go beyond 30. 35 is a reasonable number.
Okay.
Okay, so you don't really have to go up to, you don't have to run the number of neighbors. I actually ran it from 1 to 15, I believe. Yeah,
Yes.
1 to 15. Okay.
Mhm.
So, you don't really have to go beyond 30, 35 for a big data set.
Okay.
Even which had 5 million examples. Because if you think about it, like finding the nearest neighbors is the most expensive thing in K nearest neighbors.
Okay.
Okay.
So even if I have 5 million data sets, like I can run 30 to 35 neighbors, and then
Correct.
with a randomized search of CV, I can get the nearest thing, and then I can do my works.
Correct.
Okay.
Absolutely spot on. The reason is, like, I'll tell you this, okay? Maybe we can have this discussion. Let's say if I'm interviewing you guys right now. Okay, let's say you are doing this K nearest neighbors and you are using So I have a data set of 100 examples. Okay. What is the highest number of neighbors possible?
100.
100, right? 100. You'll be
Okay.
using all of them, right? In the
Okay.
training set. Okay.
Okay.
Let me give you a sample. What do you think it will predict? If I use 100 neighbors as my, as I use 100 nearest neighbors to get my predictions, what it will predict? Think about it. In plain words, what it will predict. Let's say you're doing simple averaging.
It will take the average of my
100 values, right?
Yeah.
100 training outputs. It will take the average of all of that. Is that part clear to everyone?
Yes.
Okay. Now think about it. I give you a different sample and you are still doing the same thing, 100 nearest neighbors. What will be the output? Will it be changing?
No, it will be same.
So can I say that this is a constant model?
Yes.
Does it make sense? So if you look at more number of neighbors, you are tending towards a constant model. Does it make sense? Is a constant model good?
No.
No, right? Okay. Let me give you one more example where we are looking at the other end. Let's say I use one nearest neighbor. Okay. What will happen now? The predictions will change drastically, right? Because now they'll be coming from the closest sample only. Yes or no?
Yes.
Okay. Now they'll be coming from the closest sample only. Okay. Now there is this catch. Okay. There is this catch. Please listen to this very, very carefully. And this concept is called as overfitting. Okay. All right. Please listen to this very, very carefully. Okay. So I am taking this example where I have 100 training examples. Okay. Let's say I choose one of the 100 training examples and try to predict on it. What will be my result? I'm doing one nearest neighbor.
The correct value, whatever is next.
Whatever is next to it, because this sample is present in the data set, right?
Yes.
Okay. So can I say that if I use one nearest neighbor on any of the training samples, what would be my error? You can compute mean, absolute, sum of absolute, anything. What would be the error? Error is computed, let's say, as the absolute difference between actual and predicted. You're doing one nearest neighbor.
0 if the data is present in the training set.
I'm saying the data is present in the training set. Okay. So it will be 0, right?
0, yes.
Okay. So the phenomenon of overfitting says that when the model performs, okay, exceptionally well, okay, on the training set. But so let's say if I was passing the samples from the training set, okay, so I will get excellent performance, right? Every time if I'm using one nearest neighbor, yes or no?
Yes.
Okay. However, do you think k equal to 1 is guaranteed to be the best model for my test set?
No.
No.
Not likely. And that we have seen, right? The answer that we are getting is 9, 13, 15, and so on.
Yes.
Right. So most machine learning models, they suffer from this problem, which is called as overfitting. The model performs exceptionally well on the training set. However, it performs miserably on the test set. So if you want to compute the training error for, say, k nearest neighbors with k equal to 1, it will give you a 0 error. But can I pick that? I cannot, right?
Yep.
Okay. So when you are doing machine learning, which error should you trust? The training error or the test error?
Test error.
Test error only, right? But don't you think that training error is also important to some extent, just to tell how well you are learning? Yes or no?
Yes.
That is also important, right? Because if so think about, say, k equal to 3. If that is too, let's say, if that is performing miserably on the training set, so can I say k equal to 3 is a bad model? If it doesn't even learn on the training set well, don't you think it will be a bad model?
Yes.
It is likely to be a bad model on the test set also, right? So if there is an individual which isn't able to recall the topics that the individual has studied, that is a bad model, right? Even on unknown questions that may come in the exam. So it's the same concept here. The model should do really, really good on the train set and also really, really good on the test set. But if the model does really exceptionally well on the train set, but it fails miserably on the test set, then this phenomenon is called as overfitting. The other way to look at it is like the other side of it is underfitting. And this is where the model doesn't even do well on the train set. Okay. The model hasn't learned enough from the train set. Okay. So there is no point in talking about the test set. Okay. The model fails on the test set. Fails on the training set. I mean, the performance is very bad on the train set. This is called as underfitting. So can you tell me which value of K overfits typically? Which value of K overfits typically? Low values of K or high values of K?
Low value of
Low values.
Low values of K. Okay. So, and the high values of K typically underfit. Okay. That's why I said you want to find a model which is neither underfitting nor overfitting. You want to find a model which is, you can say, performing good on the test set and also reasonably well on the train set. Okay. So this phenomenon you will see in every machine learning model that I'm going to teach you from this point onwards. So if somebody asks you, which is the most complex model, what will you say? With low values of K or high values of K?
Repeat your question, please.
So let's talk about model complexity. Okay, let's talk about model complexity. See, model complexity is not model simplicity. These two are very different things. Okay, don't think about interpretability. A complex model is one which is basically trying to generalize for each example. So if you make a prediction, it will give you different values for each prediction. Okay, for different prediction or for different examples. And a simpler model is one which is going to give you almost the same results every time. So which do you think is a simpler model and which do you think is a complex model? See, when I say model complexity,
model, low value of K is a simple model, and
no, it's the other way around. See, what does low values of K mean? See, you're thinking again about model simplicity. See, what is, let's say K is equal to 1. This is the most complex model I'm saying. Do you think that using K equal to 1 is the simplest model? Think about it. Is it the simplest model? It's actually the most complex model that one can think of. Simplest.
I have a value, I'm just comparing it with single value in my set.
Okay. No, but how do you find that value? You have to compare it with everything, right? Yes or no?
Yes.
Okay. Now, when I talk about using K equals to 100, where I am having 100 examples, don't you think you have to, just use all the training examples without even making a comparison?
Yes.
Which is simpler?
100.
100, right? Do you get that now? So a complex model is one, you can say, which makes more computations.
Yes.
Okay. A simpler model is one which makes, less computations. Okay, in general. All
okay,
right?
So from my better understanding, like when the model does a lot of computation, that is the best model, and if it is doing a
not necessarily. I'm not saying that. See, we have to find a model which a decent model complexity.
Okay, so based on the
Okay.
result, we have to find out like what is
What
best
we
for-
need. Okay, what we need. See, is it always the case that K equal to 1 will be bad?
No.
No, right? Not always, right? So that's why we are doing this grid search and or randomized search. Okay, but low values of K, they have typically higher model complexity. Okay, so yes,
equal
go.
to 100 thing, I can say only when the highest value of K is same as the number of samples, then only for each value I have to take into account all the samples.
Okay, let me talk about this. Let's say if you say I take K equal to 99, do you think that you will still compare it with all the samples and still figure out the 99 closest ones and then do more computations? That's what you're thinking?
Yes. That's
okay, why don't you just remove any sample from the train set and find out the 99, take 99 samples and do the average of it? Do you think the results would differ? Would they differ much? No, right? So think of it like this. The way you can simplify the process, okay, not think of how to do it in a brute force way. See, if you always think about brute force, then K equal to 99 will have more computations. Yes or no?
Yes.
Don't think of brute force, right? I mean, think about, you're taking the average of 99 examples out of 100. Don't you think the values of any input will still be close by? regardless of the input.
Yes.
I mean, majority of the outputs that you get for any test sample will be the same, right? You're taking the average of 99 out of 100.
Yes.
Okay, very rarely they would change, and they would change mediocre, right? Because every time one example would be left out.
Yes.
Okay, so model complexity, see, I shouldn't have said in terms of complexity. It is like saying when you are looking at say more examples to make your prediction, you can say that your model is probably having lesser complexity.
Okay.
Okay, that's one way to look at it. If your model tries to adapt to every data point, then the model has more complexity. Okay, let me even simplify this even more. Okay. So imagine I give you this 100 examples. So a data set contains 100 examples. Okay, and I add now one more example to it. Okay, or maybe say 3-4 examples to it. So my data set now becomes 104 examples. Which value of k will lead to, let's say, more significant change in results? Lower values or higher values? Think about this.
Lower value.
Lower values, right? Because the 3-4 examples that you just added might become the new nearest neighbors, right? So the predictions can change drastically.
Yes.
Does that make sense? However, when you are taking the average of say 100 out of 104 now, it will more or less be the same. I mean, still very, very close by.
Yes.
That way you can interpret model complexity. If the model changes drastically on adding new examples, that is a more complex model. Okay. Does that make more sense now in comparison to saying it is more complex in terms of computations? Okay. So this overfitting is in terms of how well the model can adapt to the examples. Okay, how well the model can adapt to the examples. So which values of k can adapt significantly to the change in the training set? Lower values or higher values? Which values can adapt better to the training set? Lower values of k or higher values, regardless of the number of samples in the training set? It is low values of k, right? Low values of k can actually adapt to the training set very, very well. If you say this is high values will be like, let's say if I use everything, then the answer would turn out to be almost the same every time. I mean, the same every time, right? So you can put it like this. The phenomenon of fitting is nothing but trying to learn from the examples. So if a model learns too well, okay, then you can call it overfitting. If the model doesn't learn much, then you can call it underfitting. Okay, maybe perhaps this is slightly confusing right now. When we discuss other models, this will become more and more clear. Okay, this will become more and more clear. Okay.
So when it comes to training the model, we can't give more complex or else low complex. We have to train
because
it
low complexity can will result in even worse in the test sets, worse results in the test set. Okay. We don't want overly complex model. We don't want overly simple model. We want something in the middle. We want basically lower results on the training set. I mean, lower error on the train set and lower error on the test set also.
Okay. So we have to both we have to balance both the training and test.
Yes.
And also we can't give more we can't give, if I have a 5 million data in my data set, I can't give more training to the data set. Instead of that, I have to keep it in the medial in the middle of somewhere around, as you said, 30 to 35, so that I won't get to use a lot of time of the machine, or else I can't waste my lot of time. Forget
about computations for now. Okay. See, computation is not a problem, especially in today's era. So think about if you use overly complex models, your judgment should be based on this test set. You want to do best on the test set regardless of how you perform on the train set. But if you do very, very badly on the train set, then there is no point in checking for the test set.
Test set's true. Okay.
All right. So our ultimate objective is to do well on the test set. Okay. Now it is depending on how you look at it. So if you're doing exceptionally well, you will say that your model is overly complex. So reduce the complexity a little. So how can I reduce the complexity? Maybe increase the values of K.
Yeah.
Okay. And if somebody asks you, let's say if you're performing very, very badly on the train set, then you might want to reduce the values of K. Okay. On the
Sure.
train set, I'm saying. Okay. So that way you can argue, okay, this is what can happen and will lead me better results on the test set. Okay. And you have this mechanism of testing, right?
Yeah.
Okay. You have the actual labels of the test set. Okay. And that is why supervised learning is so beneficial, because I can always validate against the ground truths. So I know what value of K is likely to perform better even on unknown examples. Right? When I say it's likely to perform better, because I cannot say, right, for sure with a guarantee, the best performing model which I obtain will be the best performing model on the unknown examples that I see in the future. But even if I take the best, but I can maybe take, say, one of the top 5 best that I obtained, right? So I have to like satisfy my buds at some point, right?
Yeah.
I have to be convinced at some point. See, I cannot just keep on doing the experiments over and over. I have to stop somewhere.
Okay.
All right. That is what machine learning.
That's what. So we can't look for a very perfect model. We can look at like near to perfect.
Okay, we will talk about that in more detail. Okay. See, we want the best because the best is likely to perform the best in the real world.
Okay.
Right, but achieving the best might take a lot of time. So we settle with like one which is close to the best.
Okay.
One which is close to the best.
Totally.
However, one which is close to the best may actually outperform even the best if you would have obtained that. Okay. Or it may not even outperform the best, right? So there are two sides of the coin to it. See, we want to get to, let's say, good results. I wouldn't call it exceptionally greater results or the best results. Because if we strive to get exceptionally best results, there is this trade-off of time. So if you have time for offline training, try to get the best and try to deploy the best. But it is still not guaranteed to be the best on future examples.
Yes, maybe the future examples can change the output of our model.
No. What if, see, okay, so don't you realize that there is a fundamental assumption associated with supervised learning? What is that? The future examples should follow the same distribution as of the data set that you have.
Yeah.
Only in that case, the model will do well. Yes or no?
True.
Okay. So there is this fundamental assumption. This is the most important thing when you all, that you all should know. So when somebody asks you what are the limitations of supervised learning, the first thing that should come out of your mouth is that the distribution of the test set on which you are about to test should be the same as the distribution of the training set on which the model is trained. If this is different, the model will not perform well in any case. Does that make sense? Even if you do well on the train set, okay, even if you do well on the train set, are you guaranteed to do good on the test set? Even if you were underfitting or overfitting, if the test set is coming entirely from a different distribution. No, right?
Yeah.
Okay, think about you train a model for, say, Indian community, but you're testing it on, say US community.
That'll be totally different.
Totally different, right? Okay.
Yeah.
No, but let's say you're doing the same thing. Let's say you're trying to predict the weight of an individual. In US, more people are obese. Okay, so your results would always be bad. Okay.
True.
Because US people are not there in your data set, right? So this is a fundamental assumption associated with supervised learning, that the test set should be from the same distribution as the train set. If that is not the case, then the model will suffer. So your reliance on data has to be factual. Okay. The data that you collected, you have to ensure that it represents. It is sampled from the community on which you'll be applying it later. If you apply it on a different community, it doesn't make sense. Your model will definitely suffer. By the way, there are machine learning domains which tackle this problem as well. If you are interested to do more research in this area later on, the domain is called as domain adaptation. Okay. There are ways in which you can adapt to test sets even if they are coming from different distributions. This is like beyond your scope. Okay.
Okay.
Okay, there are concepts like transfer learning that you can use to make your models better. Okay, when the distribution differs. Okay, I'll give you some more examples just to discuss supervised learning in more detail. So imagine that, let's say you are training a model which can predict, say, sports or religion. If a news article is from sports or religion, let's say you collected the data from, say, any newspaper industry. Okay, maybe say you went to the Hindu and you collected all the articles, all the newspapers that have been published in the last 10 years. You trained a model on it, and now you're applying it, say, on Tribune. Do you think it'll do good?
Can you please repeat?
So let's say I'm making a classification model which predicts if the output is a sports article or a religion article. Okay, there are two categories. So you trained a model collected from newspaper articles published by the Hindu. Hindu is a very popular newspaper.
Yeah, newspaper.
Yeah, okay. So you collected maybe newspapers of the last 10 years and trained a model from it. Now you're testing it, say, on Tribune. The Tribune is another famous newspaper.
Okay.
Or let's say the Times of India. Okay.
Okay.
So you are trying to test on that. Do you think the results would be good?
No, because the news may differs from.
No. Your goal is to just predict between sports and religion. Okay. Can I say there will be, on an average, good? On an average, I'm saying not too good, not too.
Yeah.
Not too great,
Yeah.
not too bad. Okay. Why is that? The results are not as exceptional if you were to train later on, let's say, on the Hindu articles. Let's say if you test it later on the Hindu articles, your results would be great, right?
Yeah.
In the future, if newspapers are to be published in the Hindu, if you test your model on that, don't you think your results would be better than the results on the Times of India?
Yes.
Okay. Why is it happening? Because see, when we talk about these data sets, we are going to use features, right? What will be the features from text? The words, the vocabulary that people use. Vocabulary of the editors, the authors of Hindu might be very, very different from the vocabulary of the Times of India people. So the features would be very, very different. Okay. So the feature values would be very, very different. So even though they use, let's say, a different synonym for the same word that you use, okay, the model is not going to capture the sense. Okay, machine learning models cannot capture sense. You will see that. Okay, especially when you process raw text, they forget the sense. Okay, but you can always make the models better if you can capture the sense, and that is what some idea of transfer learning is, domain adaptation is. Okay. All right. So there are multiple branches of machine learning beyond the scope of discussion, but they are trying to tackle each of the problems in machine learning domain. Okay. Their motivation comes from the fact that, okay, if we can try to tackle some of the problems from supervised learning, unsupervised learning, and so on. And this domain adaptation and transfer learning tries to do it from the perspective of the distribution. The distribution has to be the same.
So this domain adaptation will work in both ways, like in supervised learning and unsupervised learning. It works in both ways. Okay.
Yeah. You can do it from both perspectives, just by looking at the features and also by looking at the outputs, including the outputs essentially.
Okay.
We will discuss that in more detail, the idea is like this. All right. So let's discuss our next model. Okay. So this is going to be. I have to omit a lot of details, because I have limited time with you guys. So what I'll do is I'll show you what internally a method is doing. I'll discuss the theory part in some more detail, but I'll be concise. Okay, I cannot discuss the whole of the derivations, whole of the theory from every standpoint, like the way I've done it for k-nearest neighbors. See, I wanted to lay the foundation for one machine learning algorithm very strongly. I will share some documents that probably you can read, and if you want to discuss more, I'll be available for discussion. I typically ask in the first 30 minutes or so, if you want to discuss anything, let's discuss that. However, for our next set of algorithms, I'm directly going to tell you, okay, this is what, if you do this, you'll get this. If you want to read how this is done, I'll share an article with you. Does that make sense? Will that be all right, first of all? Or do you want me to show everything in detail? Because see, I don't have 6 months just to teach you ML, because I take 6 months to teach ML to my students. Like I'm in an academic setting, so here for a semester, I teach for 6 months. Okay, I take around 80 hours just to teach ML. And you are going to do that in probably 20 hours. So I have to summarize all those details and share that with you. Does it make sense to you? So I cannot do everything, right? You also have to put in some bit of efforts. I talk a lot about research also, which is not the same in your case. So I'll be sharing the details that you guys require from the data science perspective. Okay, and if there is something additional that you may want to explore, I'll tell you this is the article which you can read and you will get all these details. Will that be fine? That will save me a lot of time and you guys as well. But if you want me to discuss it, I'll discuss that also. Okay. Then I'll ask for some extra sessions from Google people, and they will happily oblige. Okay. So I'm just giving you a heads up. This takes typically a lot of time. Okay. Will that be all right? Can you guys give a little bit of reading on your end or not? See, again, I'll put it like this. If you think that you can become a good data scientist just by watching me do it, trust me, you cannot. You'll forget everything in the interviews. So you have to practice, you have to read. Okay, so when you go back, please spend some time, at least 20 minutes per day. Okay. All right, let's discuss our next algorithm, which is called as linear regression. This is, again, one of the simplest algorithms in machine learning. What I'll do is I'll show you. Okay, let me create a data set very quickly. So there is one more function in sklearn datasets which can help you create your own datasets quickly. Okay, so I want to get, or rather, let me take the dataset that we have. Okay, I have this x and y, right? This is your x. I'm going to take one feature. Okay, and let me take 100 samples, 100 or maybe say 20 samples. So I'm taking 20 samples. Let's say this is my the first input. Okay, this is my, say, x. Okay, all right, and my output is the diabetes values for the first 20 samples. Okay, I'm going to plot this. Let's look at this. So plt.scatter of x and y. Okay, so what was the first feature? Does anyone remember?
It should be small y.
No, what was the first feature? Yeah, I'll make it small y, but what was the first feature? Does anyone remember from this data set?
Age.
Age. Okay, so we are looking at the age of the individuals, which has been essentially standardized in the data set that you have. Okay, and you can normalize it if you want here as well. But we are looking at one feature. Do you feel that if there is one feature, is there a need for normalization or scaling?
No.
If there is one feature, no, right? So no need to standardize or normalize because I only have one feature. So we are doing univariate regression right now. Okay, so let's plot it. Let's see the results. Okay, this is how the data looks like. Okay, I mean, it doesn't serve my purpose. Maybe I'll take another data set. Okay, I want to be very precise about this. Okay, I have one data set which is like this. I'll put it into a shared folder also. Okay, so let's try to predict the salary of people from, okay, it was called as salary data. Let's try to predict the salary of people from their experiences. This is a real data set, by the way. Okay. So this is my data frame. I'll show you the first few. Let me show you the entire data frame. Okay, it will not print everything. So this is the data frame that we have. It has around 30 samples. And you have years of experience as the input, and this is the salary, okay, of people. This is in dollars. Okay, so my x is this df of years of experience. Okay, so I will take this df of and my first column will be df of columns of 0. Okay, Please note that I'll be reshaping it. Okay, so I'm reshaping this because what will be the shape of the input? What will be the shape of the input? Number of sample times and number of features. This is expected, okay? Input should be of this shape, okay? With one feature, if you just get, right, it will be only number of samples, comma. So I'm just reshaping it. And if you look at y can be just number of samples, comma. Okay. Okay, so this is fine. Okay. This is your output, which is number of samples, comma. All right. So let's plot this x and y. Let me get the values from it, okay, because then both of them will be numpy arrays. Okay, this is your data. Okay, let's see this data. Okay, let me label it. This is your axis x1. This is your axis x2. You can say the output y. Okay, so so let's say x1 is your experience, and y is your salary. All right, and let me say plt.title predicting salary from experience. Okay, so this is what we want to predict. Now, for this type of model, I mean, if this is the data which is given to you, do you think I can use k nearest neighbors? I can, right? Yes or no?
Yes.
Okay, that's a good way to do it. But is there anything that comes to your mind just by looking at this visual representation? So I can use any other way of predicting. Think about this. What can you do for this plot so that you are able to predict?
But most of them, they fall under a straight line. And
yes, that you can use. So let me tell you what is the advantage of predicting it through any function. Okay, let me ask you this. Let's look at this point, which is somewhere here. So this must be around 11 comma something, right? 11 comma close to 1,20,000. Yes or no?
yes.
This point 11 comma this. Okay,
Yeah.
I use this data to predict. I use this entire data to predict. Okay, if my years of experience is say 50, what should be the salary prediction? You can use say k equal to 1 as the number of nearest neighbors. What would you predict if the years of experience is 50?
With K1, you'll have 1,20,000.
Because this would be the closest, right? The furthest sample on the right. Does that make sense?
Yes.
Okay. Think about a sample which is say to the below. Let's say this is somebody's 0.1 experience. What would be the prediction? Close to 40,000?
40,000, yeah.
Okay, makes sense. Okay. Now, do you think that even if I go with 100 years of experience, will my prediction change with respect to this?
No.
No, right? So can you see that k nearest neighbors has a big problem? It cannot generalize outside the training data.
Yes.
See, even if you take multiple nearest neighbors, do you think, so let's say the minimum value of your output, the minimum value of your y is this, maximum value of y is this, okay? Do you think that the prediction will ever come out below this or before this?
No.
Below this or beyond this? In any case whatsoever? No, right? Does that make sense to anyone? For any value of k? See, average is going to make it even smaller. Okay. Any type of averaging, even if it is distance averaging, it is going to make it smaller than the maximum value. So do you realize that k nearest neighbors cannot generalize beyond the training data? So the output of k nearest neighbors, the predicted output of k nearest neighbors, okay, cannot, is always within the range of the training data. Yes or no? Is
Yes.
it clear? Okay. Now let's think of doing the prediction with the help of a line. And if I do it with the help of a line, don't you think I can extend the line and still predict? Let's say I'll show you how to make this line. What is the equation of the line?
Y is equal to mx plus c.
Y equals to mx plus c. See, since we are using this, axis as x1, can I write it as m times x1 plus c?
Yes.
And since we use this symbol y for actual values, can I write it as say y hat? Does this make sense?
Yes.
Okay, so keep this in mind. I'll be using this notation, more often than not. What is M? Or let's talk about C. What is C? In general,
Fine.
C is the intercept. So C is the point where your line hits the y-axis. Okay, so if the line passes through origin, what is C? If the line passes through origin, what is C?
0.
0. Okay, so this is the C is the value, the point where your line hits the y-axis. Okay, it can be negative or positive depending on where it hits. Okay, keep this in mind. So in my case, y is the output, right, where it hits the output axis. Okay, and what is M? M is called as the slope. And what is the slope? The tan of the theta. Okay, tan of this theta. Let me call it like this: tan of theta. And theta is what? Theta is the angle the line makes with your, the line makes with your x-axis. Does that make sense? Yes or no? Is this part clear or not? Okay, we'll discuss this part in more detail. I'll move to the whiteboard and then we'll discuss it. I just want to show you this. Okay, like you can get this value of M and C from the data very, very easily. Okay, how you do that is you use this algorithm called as linear regression. So this algorithm is present in the library linear model. You use this algorithm called as linear regression. I'll show you the derivation and everything for how it is obtained. Okay, but since I have limited time today, I'm just going to show you, okay, how you obtain it. So this is the model linear regression. We fit it onto our data. What should we supply to this?
X and Y.
X and Y. Okay, so we supply this X and Y to it. And this model predicts two things: the intercept term, which is your C. Okay, so this is your C. Okay, so I'll just save it as C. Okay, and the M value is present as the coefficient. Okay, it's also called as coefficient for feature x1. This is the coefficient for feature x1. Okay, you can call it the slope in this case. Okay, this is your coefficient. It is printing an array right now, so I'll just print this column 0. Okay, see, it is printing an array right now, so I'll print this 0th value. I need the value. Okay, so this is your M, by the way. All right. So I will try to draw this line on top of this data. Okay, and let's see what is the line that we get. So the equation is this mx plus c, right? So I can say plt.plot. Okay, and I can plot on this line. So my x is still x, and you can say m into x plus c. Okay, m into this x plus c. Does that make sense? Yes, people. Is this part clear? So wherever the predictions are, see, wherever these predictions are, okay, let me show you what mx plus c is. Okay, so this is your data in x, which is the, you can say, experience values. And if I do this m into x plus c, these are the values. So these are the predictions. Okay, sorry, m into x plus c. These are your predictions. Okay, so I'm going to connect all these predictions. Okay, I'm going to connect all these predictions. And don't you think it will give me a line? Because the equation is of a line, right?
Yes.
Okay, so I'm going to predict with the help of this line m times x plus c. Do you see that? Okay, this line is fit very nicely. Okay, now you give me any value of this x1. Okay, you give me any value of this m times x plus c. Don't you think I can even go outside the training range? Let's say if x is 50, let's see what is the prediction. This is 498290. Do you see that this number is actually beyond the data set? Okay, where is this number? The maximum of y that I showed you, this number. Do you see that this is beyond? Yes or no?
Yes.
Okay. So see, if you want to simply predict, you can use the predict function also. Model.predict, pass this value as 50. Okay, you'll get the same thing. It is doing actually mx plus c. Okay, it is actually doing mx plus c. So you can get the predictions outside the data set also with the help of such a function. And I will show you how to fit, say, squared functions, cubic functions, parabolic functions, and so on. Okay. We'll see different types of functions that you can fit to it. Okay, I have a question now. So currently we are fitting a line. Okay. Can you visualize the data in more than 3 dimensions? Can you visualize the data in more than 3 dimensions? Is it possible? Can you make
No.
more than 3 dimensions? No, right? Okay.
No.
So see, I can, for this line, don't you think I can predict? So I can break this data into train and test with the help of train set. I can, find the best line, and on the test set, I can predict what are the predictions with the help of this line. And then I can compute mean absolute error, mean squared error, and so on. Okay. So I do that for a line. Let's say I do that for a parabolic function. So I try to fit a parabola and I try to get the results on the test set. So what do you think will be better, parabola or a line for such type of data sets? For this given data set, what would be better, a line or a parabola? What do you think? For this type of data set, what would be better, line or a parabola?
For this example, line is better.
Line would be much better, right, than a parabola. Parabola would actually be like this. I mean, it will go like this. Parabola would go something like this, which will be a bad result. I mean, bad for some of the samples. So like you can visualize this, right, in this case. But if you have more than 3 features, what would you do? I mean, more than 2 features, what would you do? When I say more than 2, which means 3 or more. See, if you have 2 features, you will have x1 on one side, x2 on one side, and y on the other. So you can still plot it because that will be 3 dimensions. If I give you 3 features, will you be able to plot?
No, not.
No, right? Because you will need one axis for the y also, right? And that makes it 4 dimensions. So you cannot plot it for more than 3 features. I mean, more than equal to 3 features. Okay, for more than 2 features, you cannot plot. So how will you know which type of model is better? Is it linear? Is it parabolic? Is it cubic? What is better? You can check on the test set, right? So even though you cannot tell visually, I can see this visually and tell, right? Okay, linear is better. So I don't have to check for squares and cubic. But if you want to do it in general, so this is like grid search. Which type of function should I do? Should I do linear? Should I do square? Basically quadratic, cubic? What type of function should I do? Okay, so we'll see all of that in the next class tomorrow. Okay, but this is how you use it. I'll show you how to obtain these MNCs. Okay, I'll show you how to obtain these slopes and the intercepts. Okay, there is a vivid maths behind it. Okay, so we'll see all of that. Okay, maybe I can discuss some of the motivation behind the maths. So yes, go on.
Like for model K nearest neighbors we were doing, we have metrics to evaluate the
model.
The model is
correct.
Metric evaluation was there. Here also, do we have some
same? See, it's a regression data set, right? So we'll be evaluating it on the same using the same metrics.
Do we have the same things like mean absolute and
correct? It's so for all the regression tasks, we'll be using the same metrics. Okay, so all those are generalized metrics that we have studied, not just for k nearest neighbors. Okay, they'll be used for any regression task. All right. Okay. Now, can you tell me? So, see, this is one line which I came up with. I mean, I didn't come up with, but the algorithm came up with. So, let's say there is another line which I draw. Let's say the line is. I'll show you this line. Maybe I'll try to connect on top of it. Okay. I'll try to make one more line on top of this. Let's say the line is. So, I'm going to connect 2 points. Maybe say. Say 1, so at 1, the value is maybe say 30,000, and at the next point is say at 11, okay, and the value is maybe say 1,10,000, maybe say 1 lakh. Okay, so this is another line. Can you tell me which line is better visually?
The blue one.
Why it is better than the orange one?
Because whatever is my training data set, maximum points are around that line.
Okay, so can I say that an objective to find this best line is to find the distance between these points and the line which minimizes it is the best fit line.
Yes.
Okay, and that is what we will see tomorrow. How to find that line which minimizes the distance between the given points. Okay, so this is the motivation behind how to find the best fit line. All right, so we'll try to find that line if find that line which is closest to all the points, which is closest, the sum of the distances of that line with respect to the points has to be what, minimum or maximum?
Distance is to be minimum.
Minimum, right? So we will try to find the line which minimizes the sum of the distance with respect to the points. Okay, that is what the objective is. So we will talk about function optimizations tomorrow. Please read about differentiation. Okay, revise differentiation. Okay, you should know some basic properties, how to differentiate some functions. Okay, so give a quick recap of differentiation. It will not take you 20 minutes or more than 20 minutes. Okay, revise differentiation. At least some basic rules, how to differentiate a function. Okay, why do we need differentiation? What does differentiation give us? Okay, so basic things. It will not take you more than 20 minutes. So have a recap of differentiation before you come for the next class. If you don't, if you do not revise some of the things, you may not be able to follow. See, this is something which is taught in 8th, 9th class. So I will definitely give you maybe a concise description of what differentiation does. But I'll not be able to explain each and everything related to differentiation. It's not a calculus class. Okay, so revise differentiation to some extent. See, if you want, I can skip all these details and directly move to the implementation without caring about what is happening internally. Do you want that? Tell me.
No.
No, right? So that's why I'm saying, invest a little bit of your time in some bit of reading, revising some of the things that you have studied, maybe 10 years before. So study all of these things, okay, before you come for the next class. This would make your job very, very easy tomorrow. Okay, basic differentiation I'm asking. Okay, and maybe you can also include partial differentiation also. Okay, partial differentiation is not is not different. You just need to know the difference between regular differentiation and partial differentiation. Okay.
Okay.
All right, I'll put this in the shared folder. Any other questions that you guys have? Yes, people, any questions?
No.
Yes.
What is the duration that we can expect for this machine learning modules?
So whatever is the duration that is mentioned to you guys, maybe say 4 to 6 hours extra.
Okay.
See, it is actually as per you guys. So if I'm able to maintain the same speed, I presume it will be like 4 to 6 hours extra. If not, then if you guys are able to catch up easily, then I'll be able to cover it in the same time frame. Okay, so maybe just 3-4 sessions extra, maybe 1 week extra. That's what I'm predicting.
Okay. That's not an issue.
No, it will not go beyond 2 to 3 weeks. No. They will not even allow this. Okay.
Yeah.
Okay, because it's my job to finish it in time. So I'm saying so that's why you said, see, I have to limit myself, right? See, maths is like so vast. You can just go and go and go. There is no end to it. All right, so I can discuss what has happened 50 years in the past. I can literally discuss that and tell you about how things have changed over the years for every particular topic. However, this is not something that you need. All right. If you were to do a PhD with me, then I could probably discuss all of that, but not from the data science perspective.
Okay.
All right. So let's meet tomorrow. Let's try to discuss this algorithm. The simple motivation is we'll try to find the line which is the closest to all the points. Okay. So we'll define an objective and we'll try to minimize or maximize it. And one way to minimize or maximize a function is by doing what? This is what you have studied probably before.
Okay.
What do you do if you want to minimize or maximize a function? Okay, let's talk about this. Let's say there is a function called as 3x squared plus 6. I want to know at what value of x this function is minimized. At what value of x this function is minimized? Can you tell me the value of x? Minimize this function with respect to x. How do you solve such problems? Does anyone remember? Okay, at least you can do this heuristically. Put different values of x. At what value of x do you think this function is minimized? Okay, what is the value of this function at 1? It is 9. Can you put
9.
some other value in x and you can get the minimum value? You can get a smaller value than this.
0 minus
0.
0. See, if you
Yeah.
put a minus, it will still be higher. The answer is 0.
Yeah, 0.
Okay. So essentially, how do you solve such problems? Do you remember?
Substitute, we will give.
So you cannot
values
use,
for-
I mean, if I give you a complicated function, would you try infinite substitutions?
Differentiation.
Differentiation. That's why I'm saying, recap this, revise this. Okay. You differentiate it and then you double differentiate it. If you can, I mean, I'll teach you all these things, but please revise it. Okay.
Okay.
That
sure.
way I'll say it'll save me a lot of time. These are concepts taught in 6th class nowadays. In 3rd class, sorry, one of my nephews is in the 3rd class. She knows about it. I'm not lying. She knows about it.
Yeah. Nowadays the CBSE syllabus.
So the
is different.
CBSE and ICSE have gone too far, in my opinion. Okay. This is what we used to study in 8th class. Okay. But now it is taught in the 3rd class. I mean, my mom used to teach me these things, but now she is even unable to, teach like when my nephew comes over, she asks all these questions, but my mom is unable to answer all these things. She knows quite a lot. So, kids nowadays are, they have been trained so
Yeah.
well. Okay.
Next level.
Yeah. Next level. Yeah, for sure.
I
Okay.
think this differentiation and all those things where I've studied in 11th or 12th, and I won't
No
say that I
problem.
studied, I skipped actually. Now I'm paying for that, I think.
No, maybe see, it will not take much time. Don't worry.
Yeah,
We'll not dive into this in detail. The reason I want you to study this is like when you read something on your own later on,
Mhm.
and you will see big derivations. So
Yeah.
don't get, I would say, overwhelmed by this. Like when you see mathematical derivations, like people, they have a little bit of fear, right? Like,
True.
but it's so simple if you understand the basic roots. Okay. If you want, I'll do some basic derivations for you guys and I'll show you, okay, that's what this function is also doing. Okay. So, but after a while, I need to stop, right? I cannot discuss the whole of ML, like from the theory standpoint. That again would cost me,
Lot of time.
lot of time.
True.
So, all right, guys, I'll stop here and see,
Okay.
there is always
And,
a time for chit chat. Yeah.
Yeah, and also I just want to ask you that actually I've told you, right, like we have assigned front capstone all those
Mhm.
like basic it's related to the basic system requirement on all those. Like I'm having a very pretty old laptop, like it's having i3 and 4 GB of RAM. Like for this small project itself, my Python was saying like space requirement was not good and all
My
those.
recommendation is use Collab for this. Okay. The only bottleneck that you might face is every time you restart Collab, then you have to mount the directory and you have to
Okay.
rerun all the cells,
Okay.
right? That would be just maybe 5 minutes. Other than that, Collab is more than sufficient for it. No need to buy anything else.
Okay, so instead of using PyCharm, I can use Collab itself.
Yeah, use Collab. Okay, that has around 8 gigabytes of RAM and some GPUs as well if you want to leverage those. So it's pretty decent. Okay. For
Okay.
any capstone project, this would be sufficient.
Okay, because like I thought of using the IDE, so that I'm asking because
No.
like,
IDs would actually make it even more, I would say,
worse.
I mean, more worse for you.
Okay,
Yeah.
okay. Because my system was on today, I won't know that you believe it or not. I think I woke up by 4, and then from 4 I was sitting on my laptop and doing those things. My laptop was, literally froze for some time. So that's what I'm
Okay.
asking.
What operating system are you using? Windows 10?
Yeah, Windows 10.
I mean, probably maybe switch over to any Linux based. They don't utilize much. I mean, space in your RAM.
Okay.
Maybe switch to Ubuntu or any Fedora flavor, Debian. Anything is fine.
Mhm.
Ubuntu is that is something which everybody prefers. So maybe switch to Ubuntu. It will not take you much time to adapt, and it
Okay.
has everything that Windows has.
Okay.
Has everything that Windows has, and it'll
But
take you maybe 30 minutes to format it.
this Google Collab will also help us to.
Yeah, it is an
work
alternative
on-
for you. Yeah, it is an
Okay,
alternative.
but the only thing is I have to run it again and again if I'm going for.
Yes, I mean, if you basically if you want to rerun this task, right? Okay, you will have to rerun all the cells again.
Okay, so if I'm putting all those in a one cell, then it'll be easy. But if I'm
no, I'm saying when the next time you start,
Mhm.
you have to rerun everything.
Okay.
And so there is this. So once you make the code, right? I mean, even if you make it in your system, if you close Jupyter Notebook, you have to rerun cells, right?
Yeah.
So there also you will have to redo it. That's what I'm saying. You can put it in different cells, but you just have to redo it. Okay. That's the only thing I'm saying. And Collab will require you to mount your directory every time. You will understand the concept of mounting when you upload some data over there.
Yeah.
Okay.
So that what do you say? Like if I'm uploading any kind of datas or any files into it, if I'm disconnecting from the collab, it will automatically delete it. So instead of that I have to mount it, right?
You have to mount it again. Okay. So you basically, if you want to avoid that problem, also have a directory in your drive, and you can use that code which can mount from your drive directly. Okay, it's just a 2 minutes task. So every time you run that cell, it will take you 1 to 2 minutes. That's it.
Okay. Sure, Santan. Thank you.
Yeah. Okay.
So Dinesh, what is the status of the capstone project?
Yeah, I would say I was about to complete it, like due to my work and all the sites said, right? Like I'm in a dilemma that my work will be there or not. So that I'm
What
having
happened? What is the
little
update?
time.
You're on the rolls or like what?
Still my logins were not working. I'm just simply sitting and waiting for the calls and all.
Why don't you guys ask for an extension if it's taking too much time?
I don't like.
They will provide it for sure.
Oh, okay. If it is, then I'll.
No, they will provide it for sure. Just let them know. Just let them know.
Sure,
so that they don't. I mean, give you a penalty for that.
Okay.
So
because this work and I have, when it comes to my scenario, I have to concentrate on my work at the same time at the course. So because of that, I'm being a night owl. Sometimes I'm working in a night shift already. So
don't overburden yourself. Okay. I mean, ask for an extension. They are very considerate.
like my work was, I've rushed up my work and all those. I've stepped by 12 and then I woke up by 4 and I'm working. And then by 3 I have a meeting and all those things. I'm just like
just ask for an extension. Okay.
Yeah, let me do it then.
You don't have to give an excuse or anything. Just ask for an extension saying that my schedule is hectic for the last few weeks. So I'm unable to cope up with the assignments. Give me some more time. That's it.
Okay, fine then. Because like I'm getting 4 hours of sleep every day, and it's
don't do that. Health is primary. Okay, forget
I was
everything
literally
else.
going sleep when I'm working, or else in a classes like I'm washing my face and all those I'm doing. It was like, when I was in a college, I used to do all. Like,
Dinesh, I need to stop here. Okay, I'm sorry. No, I can chit chat like throughout the day. Okay, I actually am in a hurry. I have another class at 11:30. I need to take a break, go to the washroom, and come back.
Yeah, I do.
So can we contact the coordinators for the extension of the project?
I believe you can. You just drop an email to them, and I think they will. So see, I'm just suggesting here. I'm not saying they will agree to it because I cannot vouch for them, right?
Yeah.
But I believe they would. I believe they would. They are very considerate in that regard. Okay.
All right, sir.
As far as I have seen, because I am not the coordinator for it. Okay.
Fine.
Don't write, okay, I am suggesting this. Okay. I'm just trying to help you here. Okay. It's better to ask, right, than not to.
True.
True, right? Okay. People are considerate in general also, not just for assignments. Okay, so take care, guys. We'll meet tomorrow and we'll discuss the concepts of linear regression. Please revise this differentiation to some extent at least. That will help you for sure tomorrow.
All right. Thank you.
Bye, everyone. Yeah, take care. Yeah.